Good morning and welcome. My name is Mark Richardson, Marketing Manager with Vibrant Technology, and I welcome you all to another MEscope ODS webinar. And joining me today is my father, Mark Richardson Sr., the CEO and founder of Vibrant Technology, and Brian Schwartz, the Director of Engineering Applications. You might, if you are a current MEscope customer, you would definitely have talked to Brian or you've exchanged emails with him. He is our lead support man, so anytime you have support issues, Brian Schwartz usually is the man you're talking to. So we welcome both of you, and we welcome everybody to today's webinar. A couple items before we get going here. We are recording this webinar, so we will be posting this out to our YouTube channel here. Early part of next week, we'll get that spun up and loaded onto our YouTube channel so you can go back and review anything you have missed. During the presentation today, we will keep everybody on mute. We have a fairly large crowd today, but we will keep everybody on mute until the end. And then if you do have questions, please type your questions into the GoToWebinar box there on the right side of your screen, and we'll get those questions answered for you. Today's topic is using a cell phone video and ODS correlation to diagnose unbalance in rotating machinery. We got a lot to cover, so we've actually broken this up into a two-parter. We're actually going to have today's webinar, which we're going to cover a lot of ODS videos, and then in the second part of that, we will get more into the ODS correlation. So we had just a lot of pieces, so we've decided to break it up into two different webinars so we can cover everything and allow time for questions and so forth. With that, let me hand things over and we will get going. Dad, take it away.
Okay, thanks, Mark. Good morning to all of you. I'm in Southern California, so you may be in a different part of the world and it might be late in the night for you. Anyway, we're going to spend about an hour today, and you can see that the topic of my PowerPoint here is a little different than the one Mark just gave you and the one we gave in the meeting announcement. I'm going to spend some time with a different version of MEscope, which we have developed, and it's for sale. It's available if you own or have a license for video ODS. Then you can use this software, and I'm going to show you how it works. It's been developed for a touchscreen environment so that you can take your iPad or notebook computer with a touch screen and your cell phone into the field, into the factory, and record a video and process it in this version of MEscope, and we call it NXT. We use three-letter words for a lot of things in MEscope. VES is our visual engineering series, which we've developed and supported for many years now. We're going into 32 years in business. NXT is a new version of MEscope, and right now it just supports video ODS. So I'm going to show you how all that works. But before we get into using the software, let's just talk about an outline here of today's presentation. We'll go through a few slides and talk about vibration analysis. Why do we even care about it as engineers or vibration analysts? Why are we employed? What's it all about? And then we'll talk about advantages of cell phone videos. Obviously, it's cheaper and non-contacting, and we can get results more quickly. We're going to talk about extracting time waveforms, or TWFs, from a video. This is very analogous and really the same thing as when we use a portable analyzer in the field or in a laboratory and we use accelerometers. The first data that we acquire from an accelerometer or a video is a time waveform. And then video ODS, as soon as we have two or more time waveforms that we've acquired from the surface of a vibrating structure, machine, structure, whatever, we call that an ODS, or an operating deflection shape. So we're going to talk a lot about ODSs. And then we do a special calculation in MEscope called an ODS FRF. So I'll take you through that. We'll calculate some of those and we'll look at them. And there's some advantages there. A little different than a FRF, or a frequency response function, different than a auto spectrum, different than a cross spectrum. We'll talk about that. Next month, and we'll schedule our next meeting early next month, so we don't bump into Thanksgiving. We'll get past Halloween, hopefully, in the US. And then we'll talk about archiving ODSs into a special database that we've developed at Vibrant, which you can install in the cloud or on a computer, on your company network, and so forth. And then we're going to talk about comparing ODSs, operating deflection shapes, and using that as a way of diagnosing machinery faults. Let's just go over a little review here of, I'm a mechanical engineer, some of you might be, or you're just a vibration analyst, but this kind of shows, and this is some very old graphics from way back when I started in this business, working at a company called Hewlett Packard, which used to be a instrument company. Now they're more or less a computer company. But when we talk about mechanical design or analysis, we can break it down in terms of motion and forces. And if we talk about vibration, then we have both motion and forces, and we call that dynamics. Now, some of you might be familiar with FEA, finite element analysis. A lot of that work is done just with statics, putting static loads on a structure to see if it exceeds the elastic limits of the materials. And FEA is used, obviously you compute for, you can, once you have an FEA model, you can solve for the modes of vibration, the dynamics of the structure, and you can simulate things and so forth. So why is vibration analysis needed? A little bit of a motivation here. The first three are more associated with what we call test and measurement, or product development, or installing new equipment or machinery in a plant. But uncomfortable to ride in certainly applies to cars and airplanes and tanks and other things. But if there's humans involved, then vibration may be excessive during the operation of the automobile, too difficult to control, again, a human being involved, or too noisy. And human beings don't like lots of noise, especially females. Okay. The lower reasons are more associated with plant maintenance, and maybe many of you have jobs in the plant maintenance department of your company, and so your concern is more with maintaining tolerances if it's a machine shop, parts wearing out too fast, or fatiguing prematurely, or breaking unexpectedly. So those are all mechanical issues that can be amplified or exacerbated by vibration. So what good is ODS analysis? MEscope from day one has been designed to show ODS data in animation with slow motion and amplified magnitude, so we can see what's going on. So once we get an animated picture of an ODS, we can, at least intuitively from the picture, our minds are very good at pattern recognition, not so good at computing numbers. But when we take the numbers of an ODS and display them on a 3D model, or in this case, we're going to look at animations of right on a video, on frames of a video. So how much is the machine moving? Where is it moving the most? What is the relative motion of one point relative to others. Now there we talk about phases. So an ODS has phase in it, and that's often an important property of a machine to diagnose machine faults. If there's a difference in phase between the motor and a pump, that is often used by machine analysts to diagnose the problem. Maybe it's a coupling problem, maybe it's a soft foot. Various problems that are associated with operating equipment in a factory. Resonances. When we talk about a resonance, we're talking about modal analysis or mode shapes, natural frequencies, damping. These are properties of any mechanical machine or device that don't change unless boundary conditions change or physical properties change. But the forces can change, and how the forces excite the structure or the machine will have something to do with how resonances are excited. Structure-borne noise, many problems are the machine itself operating like a hi-fi, like a mechanical amplifier. So it's pushing the air and making loud noises, and people, of course, will notice that just from their hearing. And then corrective actions. This is probably the most difficult part of vibration analysis. It's easy. You take an MEscope to see what's going on. It's always a little more difficult to solve a vibration problem or a noise problem. You know, if I put a stiffener between here and there, what does that do to the modes of vibration or the overall vibration or noise? If I try to isolate from forces, so let's go and talk about fundamental laws of vibration. These are 4 that I've come up with. You probably won't find them in any textbook, but this is from years of experience making measurements in the real world, looking at the data. Any structure with mass and elasticity will vibrate. So this is the assumption behind FEA and Newton's second law, where we write out equations that, and they're differential equations, that F equals ma, and the F part is what's called the restoring forces, the elasticity, the stiffness of the material, wanting to return to its non-vibrational position, if you will. So we have to have forces in order to cause vibration. We may not be able to measure them, and with a machine, we can. It's distributed. We don't know where the forces are coming from. In a modal test, we typically create the forces either with impacting or a shaker, and so we can measure the force and then measure the response and proceed with the calculation of that kind of data. These last 2 are things that I've learned over the years that many people don't quite understand. All resonances are excited at all frequencies, and we have a couple of application notes that illustrate that. So it depends on the mode shapes, it depends on where the forces are applied to the structure or the machine, and therefore the mode shape, depending on the mode shape of a natural frequency resonance, it may participate in the vibration. So the last one there, all vibration is the summation of mode shapes. Now, when we get near a resonance, it tends to dominate the vibration, but again, it depends on the mode shape. Okay, so why use a cell phone? Everyone has a cell phone in their pocket, and a cell phone is a low cost and non-contacting measurement device. So as opposed to an FFT analyzer or data acquisition boards in your computer or in a multi-channel system, those are typically more expensive. And then with accelerometers and wires, now we're getting into many companies offering wireless accelerometers, still quite expensive compared to getting a picture like this of a machine from your cell phone. And you can see there's a lot of phase here. The motor and the shroud over the belt, they're vibrating with a phase difference, and we can look at that. We can extract that directly from the time waveforms, and we'll look at that when we get into it. Here's another picture. So if you're just called out as a troubleshooter into the field or the factory and somebody says, you know, this machine is just not behaving properly, well, a picture's worth 1,000 words. There's an amplified picture of what's going on with that motor, and it looks like the base of it is perhaps what we call soft foot. The base is just moving around quite a bit. Again, all these videos were taken with a cell phone. Here's another advantage. Cell phone video can be recorded in a dark place. So many times in a factory, the machinery is off in a corner, it's very dark. Artificial lighting, jitter removal are usually not required. Now, we have customers who try to use their video equipment, including cell phones or even a higher speed camera on, let's say, a ship next to a very noisy, vibrating machine. You have to deal with the jitter that's recorded in the video, and we have ways in MEscope to remove that. Lighting is always more difficult. You got to set up the lights, you got to have power, so forth. The algorithms in these cell phones, both the iPhone and the Google phone, they just keep getting better as time goes on to remove or to take dark videos and improve the contrast, improve the light so that you can see things better. Another issue with them is that they don't sample as high as a high-speed camera. So the electronics in a cell phone, because it's sampling at a lower frequency, gathers more light and the videos come out a lot clearer compared to a high-speed camera. Okay, so what does it say here? Animated video ODS gives us a first look at vibration. So here we can clearly see a soft foot problem. There's an isolator here at the bottom of the machine, but it just, the whole thing just seems to be, it's not working properly. The machine itself is loose from its mountings. So again, we can bring in technicians, we can bring in clients, we can bring in management and show them some of our results and begin to discuss, you know, asset management, what money is involved in fixing this machine and so forth. Here is a picture showing amplitude and phase in inches per second, displayed right on the video. And we'll get to that as we get into analyzing some data. So I want to move along a little faster here because we've got a lot of ground to cover. But we can differentiate. Now the video itself is in displacement units, so we need to differentiate that data, and it's very simple in MEscope to do that in the frequency domain. Okay, so most vibration is either too fast or displacements are too small. And so video ODS allows you to see parts of the machine that are vibrating relative to other parts that are very quiet and not moving at all. The other advantage is we can instrument parts of a machine that cannot be instrumented in any other way. You just can't put accelerometers everywhere. Here's another example. ODSs can be recorded during normal operation. Many times production machinery cannot be shut down. The operations people are just going to say, no, we're losing money. Every minute, every hour the machine is turned off. But here's a clear case of one pipe vibrating and then another one is not. Okay, operating deflection shape. This is Another issue when you pay a lot of money for acquisition equipment. When I worked at HP back in the 70s, the analyzers were very expensive. And one of the reasons why is that all of the channels of data have to be simultaneously acquired. So when I got accelerometers, in order to look at a mode shape or an ODS, they have to be simultaneously acquired. Now there's other, you can use triggering and try to match up time waveforms with a trigger or a tachometer signal. None of that really is needed when you use a cell phone, because the cell phone pixels are not simultaneously acquired, but they almost are. And the phase difference between, let's say, the top of the video and the bottom of the video is so small, it's a matter of a few degrees, that again, for engineering work and most practical work, we can assume that the pixels are being simultaneously sampled. So the photograph is, or each frame of the video, we can assume every pixel. And typically in a cell phone video, we're talking about 1 million pixels. But once we've extracted the time waveforms, we can look at both what we call time-based ODS and frequency-based ODS. So we're going to get into some of that. Here's another advantage. Once we've extracted the time waveforms from a video, we can apply signal processing just exactly the way we apply it with accelerometer data. So we can do time domain windowing to minimize leakage. We can do spectrum averaging to remove noise, and we'll go through an example of that. So when we come out of the video, what we call the video processing in MEscope, we call it a wizard. We get DFTs. So these are digital Fourier transforms, not spectra, but it is a spectrum, the transform. We can look at auto and cross, FRFs, which is very common with modal, coherence, which is common with accelerometer measurements, and ODS FRFs. So we're going to calculate some of them. Now here's one of the drawbacks of a video. You can see here that there's a bright spot on this shaft, and as that rotates, the algorithm that extracts the vibration from each of the frames of the video is kind of paying attention to that reflected part of the shaft. And it's showing a lot of deformation around that reflection that may not in fact be true in the real world. So that's something to be careful with when you have reflections off of a rotating shaft like this. That's not realistic. That's an anomaly of the video processing. Okay, so here's the machine we're gonna look at videos of, and this is an accelerometer setup with a roving accel and a reference accel and a 4-channel. So we can, with this 4-channel acquisition front end, connected to the computer with a USB cable, we can measure accelerometer data where we can mount the accelerometer. You can see there's a few points here where we've done that. And we covered that in a previous webinar. In the next one, we might actually come back and look at some of this accelerometer data and compare it with the video data. Here's a little preamble of what we're going to discuss in our next video, or our next webinar, sorry. We're going to use the MEscope database, which we call VTMax, and some special software that we call a service. Here's MEscope over here, archiving data into this special database, and then we have another program called Console, where we can look at trend plots, and we can do something called FACS, which stands for Fault Correlation Tools. So we'll get into all that next month. Okay, let's go ahead and I'm going to bring up, this is MEscope NXT, and you can see that it's set up here for processing a raw video from a file or opening a previous video ODS project and doing some more analysis with the data. Over here, I've got recent projects, so it's a little bit different layout. Again, the idea here is that you can run all this in a touchscreen environment. So you'll see how much simpler it is, where you can just use a touchscreen computer and use your finger instead of a mouse. Now I'm using a mouse, and I might even use a keyboard here a little bit. So let me go back and just look at one of the raw videos we're going to analyze here before we proceed. I'm going to go to the desktops and webinars and today's webinar. So here's a number of videos. And these were the ones that we used for a tech paper that we recently submitted to an organization called IMAC, International Modal Analysis Conference. And let me just show you that paper real quickly. We'll come back to it though. I'm going to open it up, and so the title of this is Using Cell Phone and ODS Correlation. So very much the same topic of today's webinar. And this goes through an introduction, and here's the test article, and here's some unbalanced screws that we can screw into these inner and outer rotors and simulate unbalance. So this is something that we did at Vibrant. We use this a lot. Here's a picture of a video ODS animation. We're going to get into that in a minute. And then a description of time-based, frequency-based ODS FRS. So we'll come back to all that. Let me just put that down. And so I'm going to open up a baseline video here, and there it is. You can actually hear it because the cell phone records the sound along with it. So that's what we call a raw video. And you can see that it's, let me just do it again. Let's see if we can start it over. It's belt driven. There's a couple of bearings. There's some bearing housings. There's two rotors, and you can see on this one, actually it looks like there's one of the unbalanced screws is attached, but we'll go ahead and look at that in a minute. No, it's not. When I look at the still picture, it's not on there. So again, that's probably just reflections. That's reflections off the video or off the frames of the video. So we're going to go in and look at this in detail and look at all the vibration that's going on for a so-called baseline or a balanced machine. So let me put that down, and I'll put this down, and let's go back and wrong one. Let's open up MEscope NXT. Again, that stands for next. It used to be called touchscreen version TSV. We changed the name. So this is what we call the wizard, and it takes us through a number of steps. You can see them up here. They're adjust and crop, frames and elapsed time, grid points, scaling distance, magnitude histogram. So these are the steps we're going to go through here to begin to process this video, this raw video in MEscope. So let me open up the raw video. Here we are looking at what we were just looking at. I'm going to click on the baseline MOV. Now, this data was recorded with an iPhone, an Apple iPhone, and when in the field, you would connect your iPhone if you recorded the video with a USB cable to your computer. And in this case, I've already got I've already extracted all these videos from my iPhone, and they come in as a movie file, so .mov, and MEscope can process that and a whole bunch of different video formats. So I'm just going to click on this one and we'll open it up. So there it is. There's a frame of the video. And sometimes if you hold your cell phone at a different angle, upside down or 90 degrees, we can flip it around right here in this first step so that you can, it's right side up. So we don't want to restrict you if you have to stand on your head to make a video. All right, the first thing we can do is crop this video because we're only interested in the machine itself. So depending on how I took it in the field, I may have a lot of pixels, a lot of data in the frames that I'm not interested in. So there I've just cropped it. Let me do that again. I'll reset the crop. So this is just an arbitrary thing that I can do. Now, MEscope is programmable with what we call scripts. We won't get into that today, but I can also design a script, which is just a spreadsheet of MEscope commands, including these commands, so that I can process a lot of videos and then just crop them automatically if they're all going to be similar. Now, this data was taken with the cell phone mounted on a tripod right here in my office, and then a Bluetooth wireless device that you hold in your hand so you don't have to touch the cell phone. And it's just a start-stop device, and they're like 20 bucks on Amazon. So certainly recommend that to because if you touch the cell phone when it's recording, it will cause some shake in your video. And we'll talk about that in a second. But anyway, let's go ahead. Here we can adjust brightness and contrast, but if I were using a high-speed camera, I would probably have to use these adjustments, but with a cell phone, not needed. Okay, so here is a listing of all the frames. So this cell phone has got almost 1,000 frames, this cell phone video. So frame being the first frame here, the end frame over here, and I can, let's say I didn't have a Bluetooth device for starting the video, so I can remove some of the early frames because they may show even in the raw video that the camera's moving around. The other thing I need to set here, this is set to 240. Now that is the maximum frames per second or the recording speed. Think of that as hertz, same cycles per second, frames per second, no different. We're going to set this down to 60 because this is one of the settings in an iPhone and a Google phone, which gives it a very accurate picture. And for this machine, we'll see that we didn't need to record at any higher frequency. Now, when we convert that into RPM, multiply by 60, so that says our sampling frames per second is actually 3,600 RPM. But when we go into the frequency domain and look at the data, that's one of the rules of FFT and Nyquist sampling is we can only look at half of that. Now, I'll bring that up later because we can actually unfold the spectrum and recover the aliased orders of a machine like this. Let's move on. Next step. Now, this is something unique to MEscope. Those of you that own MEscope know that if you're taking accelerometer data, you can build models with points and lines and surfaces. This is a model in MEscope of a point grid. So what we've done here is just taken the surface of a rectangular point grid, and we're attaching the frames of the video right to that surface. So it's no different than a 3D model, a 2D surface. Again, this is all two-dimensional. And you can see that the point grid here, I've got 2,500 points. So if I'm going to measure vertical and horizontal from this video, from frames of the video, I'm going to have over 5,000 time waveforms, or TWFs, from processing as video. But let's just crank it up. You can see here that I can go, there's some limitation, but I can go all the way up to almost 13,000 points in the point grid. And what the software is going to do is take each frame of the video, which typically from an iPhone, we're looking at 1 million pixels per frame. We're going to reduce it down to, in this case, 12,000. And if I started the processing, you can see the extraction of the time waveforms is the next step here. It's going to take let me just start that and show you. Okay, so it's going to take 5 minutes to process that, but let's stop that and go back and okay, that's the previous step, back to the frames in elapsed time. Let me move forward and just reset this down to, just something for today's illustration. We'll set it down to roughly 5,000. Now I'm going to extract and we'll see how long it takes. It's going to go a little faster. Okay, 4 minutes. So I knocked a couple of minutes off. Now what it's doing is taking all 1,000 frames of the video and taking the time waveforms of the pixels surrounding each of these points in the point grid. So when it comes out of this process, I'm going to have about 10,000 time waveforms, which is a lot of data. And if I'm only interested in the vibration of, let's see, these bearing blocks or the base plate, or if this was a motor and a pump, I might only care about a couple of points on the motor versus a couple of points on the pump, so I can compare those vibration levels with industry standard levels. Again, anything vibrating over 1 inch per second is considered a lot of vibration by any maintenance department. And typically we want to see vibration levels below 1 inch per second on a machine. So we'll be able to look at all that here in a minute. While we're waiting for that, let's just go back and I'll put this down and just look at this tech paper here, and we'll talk about some of the things that are mentioned in this paper, because this was where we actually did a number of simulated unbalanced cases. But we took the data the same way we're going to look at it here. Now this is a screenshot of MEscope VES. Now it has a lot more bells and whistles, a lot more of a toolbox for manipulating the data. But when we come out of the wizard, the video processing wizard, typically what we get are the time waveforms up here, and we can animate by sweeping a cursor through them. And down below here are the DFTs, the digital Fourier transforms. And you can see we got peaks in the spectrum. So that's what we're looking for in this data. And those are called the orders. Those are specific multiples of the running speed of the machine. So this is what we call video ODS analysis, and there's a number of things here. We've already covered a lot of that. We can do time-based ODS animation. We sweep through with a cursor. We can speed it up, slow it down, change the amplitude. Typically in the frequency domain, we want to use sinusoidal modulation of the ODS data at the cursor. Here's a description. We're going to calculate some of these too. ODS FRS, a special calculation. And the reason we do this is we can differentiate this data from displacement to velocity units. So now when we put a cursor on this data, we're actually looking at velocity. Now this picture here is showing displacement in inches. But what we're also seeing, and we'll see this in a minute with the ODS FRS, we'll see the running speed, approximately 1,000 RPM. Here is an alias second order at 1,500, and then a third order at 500. So what do we mean by aliasing? Well, these frequencies are folding around the Nyquist frequency or speed of this machine, which is 1,800 RPM. Remember, at 60 frames per second, that's 3,600 RPM. This data here we're looking at in the frequency domain is 1,800 RPM. So here's a little bit of the math down here, very simple. We just simply take the second order, which would be 2,000 RPM, minus 1,800, and then subtract that from 1,800, and we get 1,572, which is exactly what we're seeing up here with the cursor position. And then the third order is going to be 3,000 RPM minus 1,800, and then subtract that from 1,800, and we get 558. So these orders are folding around 1,800 RPM. We'll look at that in a minute. This is going to be next month's webinar, where we look at a trend plot of all this data with various screws attached to the machine and various vibration levels. And this is all in inches per second. So we'll come back to that. Let's go back to our software. Okay, it's finished, and now it's on to, we finished acquiring the time waveforms. Now we're on to a scaling distance. So if we want to scale this data, the time waveform data that's been extracted from the video, we need to give it a distance. So I'm going to set the distance between 2 points, and it can be any 2 points in the frame of the video or parallel to it, or let's say in the frames or in the viewing 2D dimension. So I don't want to pick a distance that's going back out of the frame and then put in the true distance, because that's out of we want something in the plane of the video. And here we're just going to put in a distance, which we can measure with a ruler very accurately. And we've done this, and we've got app notes and videos that show when we compare these results with accelerometer data, they come out very accurately. Now, in order to look at an animated ODS, I don't even need to do what I just did there. I can just skip over that step, and the animated picture will show up just fine. It just won't be scaled. Now, here is another step where I can reduce the amount of data. I said we're going to have 10,000 time waveforms and 10,000 DFTs, 10,000 ODS FRFs. It's a lot of data. Let's reduce it down a little bit. And what I'm going to do is, this is called a magnitude histogram. So now that we got the time waveforms, the software has organized them all from the smallest displacement to the largest displacement, and then counted how many fit into each of these categories. There's 100 categories here. You can see they're bins. We call them bins. The last one is 100. The first one is, I've moved it from 1 to bin 2. So bin 1 is a large count of very small motion. So when I moved and removed that and started bin 2, you can see that a lot of these points in the video have been removed or in the point grid. And those are points that the algorithm that processed the frames of the video, it couldn't tell the difference from one video frame to the next, or it could, but those are very small motions. I'm not interested in those small motions. And it works on color. So again, if it's all black, then the algorithm is not going to show much motion in this area, because from one frame to the next, it's all black. Same thing up here, it's all gray. So let's just remove all those. We're only interested in the vibrating parts of this machine, and I can adjust this to remove all the points in the point grid that really aren't moving very much anyway. All right, I just hit the finish button. So now we're finished, and you can see this is the last step. And now here we are with our results. Let me just move this over a little bit and we'll make this a little bit bigger. And here is the animation, and it's a sweep animation through the time records. And there's thousands of them in here. Not quite 10,000. We reduced it by removing some of the points. But these actually, each data point here in the TWS corresponds to a frame of the video. So if I slow this way down, let's just decrease the speed. Eventually it will display every sample of data that it removed from the video. And if I slow it down even more, sometimes we need to interpolate between samples of data. But again, when it hits a sample that corresponds to a frame, it's going to put that frame on the point grid. So that's what we're seeing here. And then I can crank up the amplitude. Let's just increase the amplitude here a little bit. So we can see things are moving around. This pulley here is moving like crazy. The bearing is moving a lot, and this outer wheel is moving. So this is a so-called balanced machine, but we can see that a lot of stuff is moving around, even though the bearing blocks don't appear to be moving very much. Now let's go down here to the frequency spectrum, and we get a different animation. This is now the ODS data from the DFTs. And the first thing I'm going to do here is, well, I need to move this over just a little bit so I can get to this control. I'm going to display a peak cursor. So let's turn that off, and this is a little easier rather than putting a line cursor right on the running speed. Now you can see the running speed is 1001. I don't have a lot of resolution there, but it's a little over 1000 RPM, which is where the machine was running. This is the speed control here, and we don't need a tachometer or anything. The spectrum is telling us where the first order is, and that's what it looks like. Over here is the alias second order. Now we went through some of that math. We can go back and look at that again. But you can see the vibration changes a little bit, and here's the third order. How do I know that? Well, I have a cursor up here called aliased orders. I'll turn that on. Now I need to put it back on the running speed so I can see all the orders that are aliased from the running speed. There's some other peaks in here. We don't know what those are. We could examine those, but we know for sure that these three peaks, the largest peaks in the data, are due to they're the first, second, and third order. You can see the nice clean animation here. Let me crank the amplitude, because what we're going to see is so there we can really see the machine moving around at the running speed, and this outer rotor is quite a lot of motion. Let's just go, and I want to adjust amplitude and speed to show you that these are actually mode shapes. You can see, I'll decrease, but you can see a bending mode here, a bending mode out here. Let's go over here and put it on the third order. Now you can actually see this rotor deforming with another mode shape in the stiff direction. It's actually, and so is this one. If I go back here to the running speed, the lower speed, You can see a little bit of a bending mode there, but not in the stiff direction. So as we go up in frequency, mode shapes typically will show the deformation. Now this is pretty exaggerated, but you can see, a lot of motion there. Now, what about the bearing blocks? Let's just zoom it way in here so we can see how things are moving around. Not so much. What about the base plate? Well, there's a little bit of motion there. If I crank the amplitude even more, we'll see that this thing is just, now this is the balance case, so we don't have any balance weights on here, but it's pretty quiet, which we'd expect for the balance machine. A little bit of motion there. Okay, let's just put this back so it looks a little more reasonable. Now again, these are not, if I come up here, these are each of the frames of the video, so we can see the motion there a little more clearly, and you can see some motion of the bearing block. Come over here, this bearing here has got a lot of deformation going on, and of course the pulley also, and this inboard rotor has got some deformation in it also. If I go back here to we're back there, we can see clearly the mode shape of that inboard rotor. Very typical, all vibration is a summation of mode shapes. There's kind of more of just a bending mode, and then I go to the running speed, and it's just kind of a bending mode. So anyway, you get a lot of useful information out of the video ODS. Let's go now. Oh, a couple other things. Let me turn on a velocity cursor. So in the frequency domain, I can display data. So what it's showing me is the inches and inches per second. Now, that's a lot of motion there. So where is that happening? Well, I don't know for sure, because this is an envelope. This is an envelope of all the DFTs. So, a lot of them don't have much motion in them at all. There's the points of the structure that aren't moving much. Let's go pick a few points on this model and display the magnitude and phase of those points, the deflection of those points. So I'm going to come over here. I'm going to go edit point graphics. So there's my point grid again. Now I'm going to go and say edit magnitude and phase labels. And so now I've got a little clicker thing down here, a little floating box, and I can just pick some points. Let's pick one here on the rotor. Let's pick one out on the bearing block. Let's pick one down here on the base plate, and maybe one on this inboard rotor. We'll pick one on both rotors. Okay, so we got a bunch of points selected here. And so let me accept that. Oh, I need to go back to animation. Okay, I'm going to cut the amplitude down here a little bit. It's just a little too wild. Now, if I go over to under deflection and turn on magnitude and phase, there are the magnitudes and phases of the points. Now, I thought I selected one on the inboard rotor too, but we'll just look at these for a moment. So you can see this outboard rotor is moving at almost an inch per second. The bearing block is hardly moving, very low velocity. This rotor in here is got some high vibration levels, and the base plate is not moving much at all. So those are showing me from my VFT data what those points look like. Let's go and do an ODS-FRF calculation, and you can see that, well, let me just go ahead and do that because we're kind of running out of time. How are we doing on time? Wow, we've already spent an hour. Let's just do this calculation real quickly and I'll show you how it goes, and then we'll take some Q&A. All right, so this is, again, and it says select an active reference point. So what is an active reference point? Well, it's certainly one of these points on the rotor, on the pulley here. I could pick a rotor point also, but let me just pick this point on the pulley. I'll pick one up here. It doesn't matter that much, and we can come back and. Now, what it's going to do is change the block size. Remember, I had about 1,000 points. It's reduced the spectrum block size to pretty small, 239. It's going to do 25 averages. I want to put this on a flat top window, and I'll show you. Typically, we use a Hanning window for doing this type of signal processing, and that's to remove any nonlinear motion, distortion, all this vibration, and certainly modal analysis all based on linear. But let me go ahead and calculate these ODS-FRFs. Again, another linear measurement of the vibration. But the ODS-FRFs, as I mentioned earlier, have magnitude and phase. The magnitude is the auto spectrum of each point. The phase is the phase of the ODS-FRF relative to, now you can see we're back here. Let me just go and turn that off for a minute. Turn off magnitude and phase. Okay, so we're scrolling through. Let me click down here and get the animation. Now we're animating from the ODS-FRFs. You can see it's in displacement. Let me see if I can change that to velocity. I'm going to put a velocity cursor on there, and I'll hide that. And you can see the peaks are a little wider. That's due to the flat top window, and a flat top window is typically a little more accurate in amplitude. So again, if I'm looking for ODS data, let me turn on the aliased orders again. So again, same thing as we were looking at from the digital Fourier spectrum. We're getting the same kind of data from the ODS-FRFs, and I can, drag the cursor over here and animate from each of these. It's a little bit cleaner. You can see it's just a very nice animation, and you can see the mode shapes there. We can crank the amplitude a little bit. Same as we were doing before. And look at how nice and clean the mode shape is of both of these rotors at the third order. I think I'm going to stop right there, Mark, and ask if we have any questions that we can answer. There's a lot more to show in this software, but go ahead.
If you have any questions, feel free to type those in. A couple questions that came in here. First one, Randolph's asking, can you also make an operational modal analysis with the data? So OMA question.
Can we curve fit ODS-FRFs? And the answer is yes. Now I've got thousands of them here, but yeah, we're not going to go through that today. Maybe we'll do that next month. We can curve fit ODS-FRFs. My experience typically has been that if we don't compute the ODS-FRF, but a cross spectrum between a reference and roving accelerometer, these ODS FRFs, the reason we're calculating them is that what we're looking at is the auto spectrum of each of the points. Now, this is an envelope showing us the peaks in all the measurements. So we got a lot of measurements here. Some of them have peaks in them, some of them don't. And then we show an envelope so we can clearly see where the resonances, or in this case, the orders are. We're not doing any curve fitting, but yeah, exactly the same as when we do OMA curve fitting of accelerometer data, typically across power spectrum calculation. Now, the problem with that is we can't get inches per second off of a cross power because that's a product of two Fourier spectra. So it's kind of a squared or a power quantity. But mode shapes we don't care about. We can certainly curve fit them and get results. And we have app notes where we do that and recover, very accurate results. Another question?
This is more of just a comment or a reminder. We get a lot of requests for training, and I want to remind everybody, if you're looking for modal training, the best place to go is to NavCon Engineering. They are a partner of ours, and we've worked with them for years. Jim Steedman does a fantastic job, and they have a few 4-day hands-on training, modal training coming up here. There's one November 13th through the 16th, another one December 11th through the 14th, and then next year, February 26th through the 29th of 2024. And those, all those trainings cover modal testing, ODS testing, and video ODS. So a lot of what we're seeing here today. If you want to get some more detailed hands-on training, that's the spot to go, NavCon Engineering. You can get information on our website under the training tab, or you can go straight to NavCon Engineering and get details there as well. If you get any questions, feel free to reach out to us at sales@vibetech.com. Let's see. That's it for questions right now. Kind of late. If you have questions that come up afterwards, we'll go ahead and get those answered for you. Again, you can email those to us, sales@vibetech.com. We'll get your questions answered, or if you have any questions about purchasing the product, obviously. Dad, you want to go over and just show them real quick the web store while you have the control there? If you're interested in getting a license, you can always go out to our web store and pick up a monthly subscription as well.
We have a monthly, which gets you started real easily. All the functionality we looked at today, $1,000. So use your credit card, spend $1,000. You can start processing cell phone videos in MEscope. Now what you'll get is both MEscope VES it has a lot more tools for post-processing your data in it. But if you just want an animated picture, you also can download NXT from our website. So let me just go back and see where that is. I guess that's under support, right? Downloads. So you can download NXT, there it is right there. And if you have the license for what is called a VT450 package, that will allow NXT to operate, and you can use it, on a touchscreen computer or desktop, whatever, and process your videos. One other feature I didn't get a chance to show you is that we can unwrap around the Nyquist frequency, which is 1800 RPM when you record at 60 frames per second. Now you can go all the way to 240 frames per second, which is 14,000 RPM. And you can unwrap the spectrum in NXT. so that you can look at orders that are between 1800 and 3600 RPM. So that's going to cover a lot of machinery, a lot of mechanical systems, and that's why we promote. Again, you don't need floodlights, you don't need a big setup, an expensive setup. Now we offer a high-speed camera that'll sample at 1,000 frames per second. We don't manufacture them. We resell it as a kit with floodlights and stanchions and so forth for setting up the lights in the camera. So if you need to go beyond 3,600 RPM, then you're going to need a higher speed camera with artificial lighting. But boy, for troubleshooting, start with your cell phone. That's my advice.
All right, let's wrap it up there. Appreciate everybody joining us. And again, we'll get this out on our YouTube site so you can go back and review if you have any questions. And we'll see you next month where we'll do part 2 of this one.
Okay.
Have a good weekend. We'll talk to you all later.
Bye.